Today we're going to go over the Williamson ether synthesis. The example I'm using is phenacetin because it's a very common reaction in ochem lab. So the key idea is to remember that we are forming an ether functional group using a conjugate base of an alcohol, or a phenol in our case, with alkyl halide through a SN2 mechanism. So notice that our bromoethane is primary, so the mechanism is SN2. So our starting material, we have our phenol. We're reacting it with a base, and that's going to deprotonate the most acidic hydrogen, which must be this hydrogen, and I'll explain pretty soon. So once the base, which is sodium methoxide ion, is going to deprotonate, and we get this conjugate base, and then we're going to react it in SN2 with bromoethane, and we get phenacetin. So let's go to the mechanism. So when looking at our compound, we want to ask ourselves, which is the most acidic proton? Is it this hydrogen here or the hydrogen on the nitrogen? So if we deprotonate this hydrogen, we get an O-, which is more stable than an N- because oxygen is more electronegative. So it prefers the negative charge over the nitrogen atom. So our methoxide ion, OCH3, is going to deprotonate the most acidic hydrogen, this one. And so the bond breaks and the lone pairs go back to the oxygen. We draw a little arrow and we get this intermediate. The ring is still intact. And now we have an oxygen with a negative charge. So notice that whenever you're doing a mechanism, you want to carry out your positive and negative charges on both sides of the equation. So you want to balance your charges. So we have a negative here, then on the opposite side of the reaction, we should still have the negative charge. So now that we have our conjugate base because of the deprotonation that occurred here, we want to add in our bromoethane, CH3, CH2, Br, and notice that bromine carries a partially negative charge, so the carbon here carries a positive charge. So this is now our electrophile and this is our nucleophile. So we're going to draw our arrow. Nucleophile attacks the electrophile, attacking the carbon. This bond breaks, and so our final product we get is shown here. Once again, the ring is still intact. We have that's a little ugly. Okay, anyway, so we have the O, CH2, CH3. So notice that our starting material, the difference is that the hydrogen was deprotonated, and then we added in our alkyl halide. The nucleophile attacked the carbon, kicked out the bromine, and now we have an oxygen bonded to a carbon. So we have this group that came from here, and then we have the CH2, CH3 that came from here, kicked out the bromine, and we get some HBr. And that's your phenacetin synthesis via the Williamson ether mechanism.